Okay, thank you. So this is a joint work with Thomas Ehrhard and Christine Tasson, and it is about a denotational model for probabilistic functional programming. So these days there are various models that has been presented, and there will be others, I guess, in the next few years. So the key word for understanding, in my opinion, the specificity of our approach is under the name of stability. So actually we are developing a kind of stable model for probabilistic functional programming. What does it mean, stability in this setting, and why we think it can be useful for understanding the probabilistic functional program? I will try to show you in this talk, all right? So first, the starting point of our research is a previous result we published in 2014, which is about the fact that another model, that of probabilistic coherent spaces, give a semantics that is fully abstract for probabilistic PCF. What does it mean? It is mean in that model, if you take two PCF programs that may contain some probabilistic primitive over that may contain some discrete distributions. They are denoted by the same function in the model if and only if they behave exactly in the same way in the language. Okay, so that is a nice result. But the point is that it is restricted to countable data type, meaning that it is restricted to data type where ideally there are at most a countable number of values. So we can speak only about discrete distribution in this kind of setting. And now the goal of our work, of the present work, is to try to extend this approach to uncountable types, that is to uncountable distribution, okay? And the reason is, of course, because functional programming with continuous distribution is play a role more and more important in other area of computer science. Good. So let us look at the syntax that we have used to play with. So it is like something like that. We have a PCF, that is, we have the primitives of lambda calculus. We have a fixed point at any type, so full recursion. We have a bunch of constants that help us to work with the real numbers. And the most important, we have a constant representing a continuous distribution over real numbers. We have chosen in the paper the uniform distribution in the interval 0, 1, but that's not important which one we have chosen, because then with the starting from a continuous distribution, using the primitives of functional programming, you can generate many other distributions, the most common one. So for example, here you see three closed terms of type real that represent three different distributions that has been generated by using the uniform one. This is coin, that is, it evaluates with equal probability 1/2 to 0, 1. This is the normal law, and this is the normal law condition and to the interval 1 minus 1/2, 1/2. Okay, so that's okay. So we would like to interpret this kind of language. So first thing, what are the interpretation of the types? Okay, what are the object of our category? Well, the types will be interpreted by complete cone. What is a complete cone? It's simply a R plus semi-module that is a vector space without negative elements, without subtraction, if you want to be short, that must satisfy these two further conditions that are there to telling us that actually the vectors in this cone are just positive in some sense. And thanks to these two axioms, one can define over the elements of the cone an order, defined in that way, just by looking at the algebraic structure of the cone. In this order, 0 is the bottom element, so it really looks like a cone. And in addition, a complete cone has a notion of norm over the elements that must be Scott continuous with respect to this order. And that's all, okay? Thanks to this condition, the unit ball of the cone, that is the set of the vectors of norm less or equal 1, enjoys these two properties, convex and Scott closed. So if you have now a program, a closed program of type A, it will be interpreted by our model by a vector living in the unit ball, okay? And so now these two properties can be understood, even from a programming language point of view. So Scott closure means that we are closed under recursive program. Okay, we can interpret a recursive program by the suprema of its finite unfolding. And convexity means that if you have two programs of a given type A, well, you can have every probabilistic superposition of these two programs. Okay, so very natural. Let us see some example. The unit type, okay, the type that has just one value in the language, skip, is interpreted by the prototypical example of complete cone, which is the non-negative real number. The norm is the identity, so the unit ball is just the interval 0, 1. So if you have a program of type skip, it will of type unit, sorry, it will be interpreted by a scalar here, a vector here, that is a scalar, and the adequacy theorem that is behind this model tells us that that scalar is exactly the probability that the call by name operational semantics on that program will evaluate the program to skip. Boolean is the same as you take the Cartesian product of R plus, and then a pair of two real, the norm of a pair of two real number is the sum of the two. That means that a unit ball is the set of the pair, is the set of sub-probability distribution over true or false. That's until now is simple, and the things became more interesting when we start to interpret uncountable data types like the real number. Everybody hear me when I speak in that way? Yeah, it's okay? I prefer. So in the real type, so for the real number, I will interpret the type by the set of all bounded measures over the Lebesgue sigma algebra, right? And the nice thing is that this set as a structure of cone, because with the addition and the multiplication defined pointwise. But I guess it's okay. Ah, you're right. Okay, so it's okay in that way. Okay. Well, this set here as a structure of complete of semicone, of semimodule, with the addition and the multiplication defined pointwise. The norm of a measure is given by the total mass, that is simply the value of the measure over the whole set. And so the unit ball is exactly the set of measure of total mass at most 1, which is exactly the standard definition you have in mathematics of a probabilistic distribution over real numbers. Okay, so until now everything is standard. Well, so now the situation is what about functional types, okay? And in order to understand how we interpret the functional type, it's better to understand how we interpret programs. So now if I have a program M of type that take an inputs of type A and give an outputs of type B, which kind of function over complete cone is it in our model? So it is a function, right? It is a function f from the unit ball of the input type to the unit ball of the output type. And what are the properties enjoyed by this function? The first one is the Scott continuity. So meaning that it's monotone non-decreasing, so on smaller input it gives a smaller output, okay, according to the cone order. And it's commuted with the suprema of the increasing chains. So this condition here is a natural one if you want to interpret a recursion. Okay, it's a standard one in denotational semantics. But the question is to know whether this is enough to have a model of PCF. Okay, and this is not enough. Okay, it is not enough in the sense that the category of complete cone Scott continuous function is not Cartesian closed, so we cannot interpret the functional type. Let us see the example a bit more in detail, this point. So if you take the set of all Scott continuous function between the two cones, you can check that it gives a complete cone that I call it Scott AB, right? However, if you study the algebraic order induced by this structure here, that the cone that I call it the cone order, it is stronger than the usual extensional order on the Scott continuous function, okay? Because in order for a function f to be smaller than a function g in this cone, we ask not just, it must be not just that the dou function is, that the first is smaller to the second for every input, but it must be also that the difference between the two functions is again Scott continuous, okay? And because of that, we have examples of function, binary function, that are Scott continuous, but for which their carrying is not Scott continuous. Let us see the example more in detail. So I take this function here that I call it a weak parallelor. Okay, it is a weak parallelor, so it's a kind of parallel testing, but weak because it is defined on the unit type and not on the Boolean type. So it takes two inputs that are two scalars in the unit interval, and they give an output that is the result of this expression. This is also in the unit interval. Okay, it is a parallel testing because if you give value 1 to one of the two parameters, this is constant 1. Okay, so it's really like a program. It takes two arguments. It evaluates the two in parallel. As soon as one of the two terminates, it throws away the other one, and it terminates. Okay, it's a parallel test. Well, you can check that this function is Scott continuous. However, if you carify it, that is, if you consider the function that first take the first argument and wait for the second argument in order to give the final result, that is not Scott continuous, exactly because it is not monotone increasing, monotone non-decreasing according to the cone order. Okay, so something is missing. We have to add a condition, a further condition, in order to have a Cartesian closed category. And the nice surprise that we had is that this further condition is a standard one you have in mathematics, which is take the name of absolute monotonicity. A function f between cones is absolute monotone if not just the function is non-decreasing, as it is asked by Scott, but also every difference that you can write from that function by fixing a point u in the domain is non-decreasing. And iteratively, every other function that you can, every other difference that you can write from this difference by fixing a further element u prime in the domain is also non-decreasing. Okay, so this is an iterative notion. We say that a function is absolutely monotone if every nr difference is non-decreasing. Okay, so it is a standard one in mathematics, and the nice thing is that it is exactly what we need in order to have a Cartesian closed category in this setting. Okay. So at the end, we call these two a function that enjoy the two Scott continuity, absolute monotonicity, stable maps, right? Why we use the name stable? Because stability is a name that has a long history in the denotational semantics of lambda calculus, and it comes back in the 70s. Okay, in the 70s, Plotkin introduced the question about full abstraction, okay, of PCF, by looking at the continuous semantics of PCF. That is the semantics where the objects are complete partial order and the functions are Scott continuous ones. And it proved that this semantics is not fully abstract, to make it short. It is not fully abstract because it has parallel function, like the parallelor, right? And then from that seminal paper, several people try to add some condition, to add some requirement to the morphism in order to try to be closer to the syntax, to the language, to the programming language. One of the approach was given by Berry 1 year later by introducing a notion of stable semantics, okay, or a notion of stability, whose definition is apparently very different with respect to the absolute monotonicity that I mentioned before, right? Because the setting here is completely different. Is an order here, the objects are just ordered set, okay? There are no cones or algebraic structure. Well, stability was a notion that helps to throw away parallel function like the parallelor, but not exactly to catch the sequential computing, because there are other functions that are not sequential but that exist in the model. But the interesting part is that in order to get a Cartesian closed category, Berry had to change the order at the function type. Okay, you have to take not the extensional order, as in the continuous semantics, but the stable one that is defined that way. But this is not important for us. So the situation that we have here are exactly the same. We are in a situation where we have a difference between the two orders, the cone order, that is the natural one that comes from the algebraic structure of our object, and the extensional one. And since we are using the cone order, we are obliged to have a notion of function that is much more restrictive than just a Scott continuous one. Good? So actually, we can be also more precise. If you come back to the definition of our object, the complete cone, one can be more liberal in the definition of the object by allowing to study order relations defined on the elements of the points that maybe are not exactly the one coming from the algebraic structure, but are just compatible with the algebraic structure. That kind of notion has been introduced some years ago by Plotkin and takes the name of Kegel-Spitzel. Now, the semantics of Kegel-Spitzel Scott continuous function is a Cartesian closed category, and we can, in my opinion, that it can be we can think at it as the continuous semantics of probabilistic PCF, where we are doing the stable one. So what we gain by speaking about stability in this setting, right? Because it's a bit different. Well, we gain something that can be understood well if you know a bit of linear logic. Linear logic has been introduced by Ehrhard some years later, the Berry's analysis, by studying a stable semantics, a particular one that is based on coherent spaces, okay? And it is by studying the space of stable function, Ehrhard discovered that the intuitionistic implication can be decomposed into an exponential and a linear function. Why? Because Ehrhard had always in the intuition that stability has not just to do with sequentiality, thank you, but also with analyticity, with the possibility of expressing the morphism as power series. And this is exactly what is happening here. If you consider examples, so for the moment we are able to say that just in very simple examples, if you consider the functional space of the function between the unit types, okay? Here you have 5 examples of Scott continuous function between the unit ball of skip to the unit ball of skip. Among these 5 examples, there are 2 only that are stable, okay? The green one, this one and that one. And one can remark by looking at them that the stable function in this setting correspond exactly to the function that are infinitely differentiable in the open interval 0, 1, and for which they can be expressed by Taylor expansion as a series where every coefficient is a positive. Okay? So for example, this function here that is Scott continuous is not stable because it is not infinitely because we cannot differentiate it here. And these other 2 functions are not stable because they contain some negative coefficient in the power series, in the polynomials as they are. Good. So our programs will be modeled by stable maps. But is it that enough to get a model of probabilistic PCF? Not yet, because we must model also sampling. Now, sampling is a primitive which is fundamental for when you work with, when you want to encode algorithms with a continuous distribution. And how it is defined? Well, it is the possibility, if you have a term waiting for a real number, and if you have a distribution, maybe you would like sometimes to sample this distribution, getting a value, and passing the value to the term, right? And that the level of the semantics is denoted by an integral. But in order this integral to be well defined, one must be sure that the function that we integrate is measurable, right? That is that the denotation of our programs are measurable always. And this is not always the case for stable functions, okay? There are stability and measurability are 2 orthogonal notions. Okay, so there are no measurable stable map. Here there is an example, but okay, that is not very important. So in order to assure the stability of our morphism, we have to add some structure to our complete cone. We added a notion, we introduced a notion of measurability test, which has 2 satisfy some natural conditions. From this measurability test, we define a notion of paths for associated to any cone, and then the functions that are stable and preserve the paths are exactly the morphism of our model. We can prove that all the denotational programs satisfy these two conditions. Now, this structure here is very similar to what you can find in the Casi-Borre spaces semantics that has been introduced last year in the Leaks paper that probably will be used by the next talk. And it is a common instance of a general categorical construction that you can use when you have a first-order notion, that of measurability, and you want to lift it to higher order. Okay? So here there is nothing original from our point of view, from us. So conclusion, we have a model based on complete cone and stable measurable maps, which is adequate for a language like that, with a full recursion and with continuous distribution. Okay, that's all. Thank you.
Thank you so much. Right. So, any questions?
Thank you. Thanks for the talk. Two questions. So one is stability is one kind of function space that has been studied. There are other like strongly stable. Do they have other nice property in the same way stability has a nice property here?
It's a good question, but we have no idea. I mean, it's already a miracle, in my opinion, that stability comes out again in these completely different frameworks with respect to order the set.
Okay, and another related question. So if you look, it's more a curiosity, but if you look at, try to look at full abstraction, since you are using stable, do you think you will need to use some kind of version of Gustav Or for achieving full abstraction?
No,
or?
Absolutely not. I think I strongly conjecture that also this model is fully abstract with this language. Mm-hmm. But in contrast with what happens in the deterministic case, I also strongly conjecture that the continuous semantics is also fully abstract.
And what is the intuition?
The intuition is that with the probabilities, we can have separate much more the terms. So the contexts are much more powerful. So at the level of the equational theory, it's my opinion, but I have to check this conjecture, the two semantics are the same. It's just a question to have more regular functions, so be able to tailor expand them.
Okay, thank you.
That's very lovely. But can you give us some intuition behind your choice to add the condition in the ordering that F minus G is itself in the Scott space?
It's not us that we have chosen that. I mean, once you choose to consider the natural order coming from the algebraic structure, you are obliged to consider that order. It's the structure of cone that gives us the order over the function. It's not us that we can choose it.
Thank you.
So now you have this very nice semantics, and how hard is it to use it to actually prove some examples in practice for contextual equivalences? Any experience with that so far?
Not specifically. Actually, the point is that one has to compute the denotation of programs, and that you can do that by solving a recursive equation and doing Taylor expansion. Now, that can be done, or even without doing a Taylor expansion, just proving the equality of the two functions. That can be done. That can be morally done for simple types, but as the types became more complex, no experience. I don't know. So, thank you. No, that's a good question. I don't know how it mixes with the question about computability or computability of the measurements or the way one wants to represent real numbers or things like that. No, not at all. There is one thing that I can remark is that actually the structure of cone, even if the definition is very simple, is very rich from a mathematical viewpoint. In particular, the norm defines a distance for which this cone is a complete metric space. So one can be wondering to understand what does it mean, the distance between the points of a cone from the computational point of view. For example, we have a distance of the measures, for example, that can be interesting to study.
Yeah. So if you restrict to to countable data types, do you end up, coinciding with some already known model of probabilistic programs?
Yeah, thanks for the question. We conjecture yes. There is a PhD student in Paris that is proving that, and actually we should get back the probabilistic on a species model. So it's really a conservative extension of that. But the paper is still not published. It will be published soon, I guess.